Okay, how was that?
It wasn't hard, but it was long. It was long.
Yeah. Well, if you had trouble with that one, you need to work on a lot of stuff. The one on the test is harder, and the one on the final would definitely be harder. I gave you one where the function ended up being 0 a couple of the times, so it's like, you know, relatively that was a nice behaving function. Especially on the region that I gave you. It ended up being 0, things ended up canceling out nicely. That doesn't happen all the time. Okay? So if you had trouble with that one, at least you know what you need to do now for the test. So, like I said, the test covers limits, that stuff, maximums, tangent planes, differentials, that sort of stuff. The bonus is on integrals, which I did put bonus problems here on integrals. I don't know if anyone actually attempted those. But yeah, so that's just what to look forward to. So to look forward to on Thursday. Yeah, the one on the test is harder. The region is not as nice, the function is not as nice, so make sure you know what you're doing. Did you? Oh, I got your quiz, right? Okay, all right. So today we're going to move on. We're going to talk about integrals, but I sort of have a question first. Let's say in a week time, right? In a week, I know I was going to have to fight somebody, right? Like I know it's coming. There's a fight coming in a week, right? And I know, for example, my opponent is bigger than me, he's stronger, he's like more muscular and everything, right? He's like, it's like Frog, right? And then here's me, right? The skinny little yoke. He'll probably snap me like a toothpick, right? How should I prepare for the fight?
Get a big gun.
Buy a gun. Okay, without trying to get in prison. Cheat. Work out. Why would I work out?
Yeah, he really does. I don't know what the solution is. I think you should buy a gun.
Wow. I think you should buy a gun. Really? Just buy a gun. Okay, that's okay.
Probably something to do with integrals, though.
What?
Probably do integrals somewhere.
Do integrals somehow confuse him? Look at this integral. Just run away while he's looking at it. Yeah. So, so the suggestion came. Maybe I should work out, you know. But as John said, I don't have time, right? So, one, I noticed a fight is coming up, but one important thing I noticed was a weakness that I have in relation to this opponent, right? I know that where he's better than me is like, he has a lot of muscle, right? He's bigger and stronger and all that stuff. So, but the thing is, working out wouldn't be the right answer. Maybe buying a gun is the right answer, but no. I wouldn't buy a gun. I'm not going to go to prison for this guy. But working out would not be the answer. Why? I wouldn't have time, right? Because, and the reason why I wouldn't have time is because here's an area where I'm already weak in, right? It takes a lot of time to build up your weakness, right? You never want to go into a fight where you know, this is my weakness and my main strategy is, I'm going to try to fix this weakness that I have, right? That's sort of not how you want to go about it. I would think certain things like, well, you know, if he's stronger and bigger than me, he's probably heavier. Maybe he'll be slower, right? Maybe I should try to figure out some avoidance techniques, figure out how to try to run circles about that guy, work on my speed or my power, or, you know, try to do something where I take advantage of where I'm stronger than him, right? So he's heavier, he's slower. So anything that I can do to take advantage of speed rather than strength would be good for me, right? So I try to be fast, try to catch him off balance, and then try to strike or something like that. But the important thing is, you never want to approach a challenge from where you're weak. That's the important part, right? So there's a Harvard business professor, I think he writes a lot in the business journal. Peter Drucker, he wrote a book called Managing Oneself. And what he said was, most people think they know what they're good at. Most people are wrong. Most people think they know what they're bad at. Again, most people are wrong, right? So he's talking about Most people don't know themselves, right? Sun Tzu told us back in the 6th century, you need to know yourself, you need to know your enemy. That's how you come out on top. But here he's saying, most people don't actually know themselves, right? So he said, you think you know what you're strong with? Most people tend to be wrong. You think you know what you're weak with? Most people tend to be wrong, right? Like most people think they're bad at math, right? But what he says next is the important part. He says, but you can only build on strength. You can only build on what you're strong with, right? You never want to approach a challenge from a point of weakness, right? So what does this mean for us, for math, for example, or for something else? I'll give you an example. Because I tell you guys what to do, but I understand that everyone's different, so you might not even know what to do even though I tell you. Like I told you, know this, but you're like, okay. Okay, I know I have to do this, but I don't really know how. One of the ways you should want to approach it is not from a point of weakness. Approach things from where you're strong, right? So for example, for me, I actually don't have a good memory. I can't remember a lot of facts. You know, I know it seems that way, like I'm here on the board and I can, oh, this is the form for a tangent plane, this is this, and this is that. I actually don't have a good memory. It's actually a weakness of mine. So if I'm studying for a test, memorizing everything would never be a strategy I would use. It will never be like, oh, I'm weak in memory. How am I going to prepare for this test? Just work on my memory. It will never be a strategy I would use, right? I don't have time to work on my memory. Test is coming up in a week, in 2 days, right? I don't have time to become a memory genius in 2 days, right? That will take a long time. Sure, I can start working on my memory. Hopefully, at some point in the future, I never end up in this position. But I would never actually approach the challenge from where I'm weak, right? If I know memory is a weakness of mine, I'd never study for a test where my main strategy is to memorize a bunch of stuff. If my memory was strong, though, if I had a photographic memory, that's how I'd approach every test. I'd memorize everything. I'd walk into a test with a textbook in my head, right? I'd memorize all the examples, all the formulas, everything I'd memorize, because that's where I'm strong, right? So it's not just about knowing what you have to do. You have to know how you get it done, yeah?
So how do you prepare for a test with a bad memory?
Well, I was going to get to that. So now, the important thing is, sometimes your weakness will be exploited, right? You have to know, maybe I go into this fight, and yeah, I'm faster than the guy, but maybe he catches me, right? And punches me, right? So I can't completely neglect the strength component, right? I should maybe try to beef up a little bit, but it wouldn't be my main strategy. I have to have a contingency plan for what if he actually hits me, right? What am I going to do? What if my weakness gets exploited, right? And with math, it's the same thing. Yeah, memorizing a bunch of stuff is not the main way I'd approach it, but I do need some memory, right? I do need to remember something, right? I can't go on a test and reinvent calculus every time I go on a test, right? I have to have some baseline knowledge from which to springboard off of, right? So then you might say, well, okay, how do you actually approach this weakness? Well, the same way you approach anything. Approach from where you're strong, right? So I know I don't have a good memory, but I do remember some things, right? There are things where my memory is strong. I remember my name, right? I remember my birthday, right? I remember my mom's name. I remember her birthday. I remember my social security number. I remember my address. There are a bunch of things that I remember. Even though memory is a weakness of mine, there are places where my memory is strong, right? So how do I use that to my advantage, right? I'm not going to be like, oh, my memory is weak. Just do a bunch of memorization techniques. No, figure out where you're strong. You can only build on your strength. You don't build a house on a weak foundation. You build it on a strong foundation, right? Because otherwise you get in trouble. Figure out where I'm strong, right? Figure out where's my memory strong. That's the first thing I'm going to think about. And then I'm going to be like, why is it strong there? Why is it that I remember some things and not others? Why is it that I remember my name, for example? Why do you think I remember my name?
You use it every day?
I use it every day. I use it all the time. I introduce myself. I write my name down all the time, right? You'll notice that a lot of times when I'm doing some of these math problems, like when we were doing that classifying critical points, every time I do a problem, I actually write down what D is. Did you notice that? Right?
Yeah.
I remember the formula now, but every time I do a problem, I'm going to write it down again. Why?
So you don't forget.
So I don't forget, because I know my memory is weak. Therefore, I need to attack that somehow. So I figure out, when is my memory strong? Well, it's strong with my name. Why is it strong there? I write it down all the time. So guess what? I learn a new formula, what am I going to do? I'm going to write it down all the time, right? I'm going to approach the problem from where I'm strong, right? How else do I remember things? Like, how would I remember someone else's name? I don't write down someone else's name all the time. Why would I remember someone else's name? Experience, maybe something stands out about that person, right? So here I call roll all the time, so there is some repetition there. Repetition is good for memory, so I know I repeat a certain thing that I want to remember all the time, right? And some people might not even learn by writing it down all the time. Maybe you like to just write on a flashcard and read it all the time. Maybe you remember reading. It's about you have to know yourself, basically. And then you approach from where you're strong. Another reason why I remember something is just that something stands out. Right? So for example, when I was learning Calc 2, I have a bad memory. Right? I had trouble remembering the integration by parts formula. I don't know why. I know it's simple, but whatever. Right? It came with all sort of complex ways to remember this formula. Right? I was sitting with my friend one day, and I heard him mumbling something to himself, and he was just writing it down. Like, what are you doing? And he's like, he said, oh, yeah, I remember this formula. I say video, right? Like the word video, right? Like he says the word video, right? Like, what the hell? Like, what are you talking about? And it's like, well, this part of the formula says VDU. If you sort of say it weird, VDU, right? You remember that. And the way he said it just stuck in my head. Like, I remember the formula after that. Like, yeah, it's U times V minus the integral of VDU, right? For some reason, just because it stood out, I remember that, right? So if you can try to figure a way to make things stand out to you, maybe even say a formula in a weird way that sounds funny and silly, you remember that stuff, right? You write things down, right? But that's just an example, right? So memory might not be your weakness. Maybe you have a great memory, but you apply the same principle. You need to build on what you're strong with, right? Building on your weakness tends to not go well, and you tend to not have time to do it either. So, with that being said, we're going to move on. So hopefully that quiz helped you realize some of your weaknesses, and to attack them, build on your strength. Just wanted to tell you guys that. We're going to move on to 12.1. We're going to talk about double integrals. Probably won't finish, but what?
That's cool. That's why I feel for it.
Well, it is for now, I guess. The test is the main.
Except for double integrals, you should have a double decimal, right?
A double what?
Like double integrals should get double decimal.
Double less of it?
Lesson.
Double decimal.
Well, yeah, I guess I have several sections of double integrals, though. I don't want to take 2 lessons for all of them. But yes, that's very poetic. But we'll try to get through these as quick as possible. So we start by how it's developed. I'm not going to go too much into this, but let's remind ourselves of how single integrals work and sort of get some intuition behind what's going on here. The main way we developed this was back in Calc 1 when we talk about Riemann sums. Remember what a Riemann sum was?
Yeah.
Right. You have some sort of function that you wanted to approximate the area under between an interval, a and b. So your idea was you dissect this in a bunch of integrals and you create rectangles. Right? And the sum of the rectangles, sum of areas, was approximately equal to the area under the curve. Right? This was called, the sum of the areas, we called it a Riemann sum.
Do they test this on Riemann sum of the file?
On integrals, no. For double integrals, the idea is similar. Right? Which is why a lot of our formulas are going to be similar. It's based on the same idea. We are focusing over rectangles. I'm going to show you how to do general regions soon. That's the next section. But over a rectangle, let's say there's a region here that we're going to want to integrate over, right? So what happens in 3D well, I'll show you later. We basically break this up into boxes. And on each box, what we're actually going to do is erect a box that's going to come out of the board and hit our z function. So we're going to have some surface here called z equals f of xy. This is my region projecting the xy plane, right? Region projection, that's going to be an important concept, right? And what I do is I break this up into boxes, and then I create rectangular boxes that will come up and hit my surface. Right? Sort of the same idea as Riemann sums, except now it's not areas I'm worrying about anymore. It now becomes volume, right? So things bump up a dimension. Area was a two-dimensional thing. Now I bump up to a three-dimensional measure of space, which is the volume. So the sum of volumes is approximately the volume under f of xy. Right? It's also called a Riemann sum, but it's a higher dimension Riemann sum. Right? But that's basically the idea, right? So for single integrals, the physical interpretation, geometric or physical interpretation, was the integral from a to b of f of x dx was equal to the area, or the net area, under f on the interval. AB. Right? However, in double integrals, well, these guys help us with volume, right? So geometric interpretation. It might look something like this. F to b, cf to d, double integral over a rectangle. F of xy, this could be dx dy, or dy dx. This is basically the volume, or net volume, under f of xy over the rectangle. The rectangle is the rectangle defined by my x values were between C and D, and my y values are between A and B. Right, so it means I'm looking at this region, C, D, A, B. So if I look at that region D, I want to find the volume that's under my function that's over this particular region, right? Notation. Here we could write double integral over d of f of xy dA, right? So here, this tells you that D is the region you're integrating over. In this section, it's a rectangle. We'll talk about general sections later. Region we're integrating over. And dA basically means it could be either dx dy or dy dx. Later we're going to bring polar coordinates back, and we will also be able to change it to something like r dr d theta, but that's That's around 4 sections away. Don't worry about that for right now. For now, you want to think about it like this, right? So this might be a shorthand. So I can say this integral, I can actually compute it in this way. And we're going to basically talk about setting this up, right? So this is going to be the region you're integrating over will be described by your integrals. The function you're integrating is here. And dA will tell you that you're doing a double integral, which is also obvious by here. We'll be moving on to triple integrals soon, in which case dV will be what we use here to represent 3 variables. But this is a notation that you'll see all the time. It's basically a shorthand for something like this, which can actually get more complicated on the limits. But we'll talk about that later. Maybe I can talk about that. Okay, so right here. So it's basically Riemann sums. There are a bunch of forms that I can give you with the summation. There's like one homework problem where I ask you to do the Riemann sum, but it's actually not a focus here. We're going to want to do things in shorthand with. So don't want to spend too much time on the Riemann sum thing, but it's something I should tell you about. So hence, if I know my function is always positive, greater than or equal to 0, non-negative, then the volume f of x, y, dA, this is the volume under F over the region D in the xy plane. Right, so there was a problem on the quiz where actually about finding the volume. Double integral was what you should have tried to set up. Right, so basically double integral is a way to get to volume. Of course, just like the regular integral, there are many other applications that we can use it for. But yeah, the physical interpretation behind the double integral is a way to find volume. That's how you're going to want to think about it. Just like the single integral was a way to find area.
I have a real quick question.
Yeah.
You don't have to go too in depth. But what if the double integral is by volume, what if triple integral is by?
Hypervolume, like a volume in the 4th dimension. Yeah. So.
Okay. Thank you.
Basically. Right. Every time you add an integral, you increase the dimensions. That's how you want to think
That's
about
why I
it.
was asking. I don't know what is next after volume, but now I do.
Yeah, hypervolume. Don't worry about it. Right. It's not something you can visualize. It's something that you sort of just use if you need to compute it. So let's actually do a problem, maybe. Well, this is a Riemann sums example. And then I'll talk more about how to set up one of these guys to do it shorthand. But let's get to a Riemann sums example so you can do the homework and sort of see what's going on behind the scenes. Estimate the volume under f of x, y. You can also use a triple integral to find volume, but that will assume the function 1. I'll talk about that later. Anyway, f of x, y equals 4 plus x squared plus y squared over the rectangle r equals 0, 3 by 0, 2. Now you've seen this notation in your MATLAB so far, I think, but these are talking about the x ranges, and this is talking about the y range whenever they list something like that. All right, so they're saying your x goes between 0 and 3, your y goes between 0 and 2. Okay. By dividing R into 6 equal rectangles. And taking the top right corners sample points. Right, so this is sort of equivalent to me telling you use the right-hand rule, use the top right corner as the points you want to sample. So basically here's how it would work as a Riemann sum to approximate the integral. Of course, the actual integral is just a limit of these Riemann sums. So here's my region R. X values go from 0 to 3. Y values go from 0 to 2. So what we're going to do is we're going to want to split it up into 6 equal rectangles. This is a 3 by 2. I think of splitting it up this way. 2 are going that way. 2 going this way. So this is a 1 and a 2. And it says use the top right corners, which means for each rectangle, I'm going to look at the top right corner. Right? And those are going to be the corners that I'm going to project up to hit my function, and then I'm going to evaluate the function at those points. So this is the coordinate 1, 1. This is the coordinate 1, 2. This is the coordinate 2, 2. This is the coordinate 3, 2. This is the coordinate 2, 1. This is the coordinate 3, 1. Those are going to be the guys I'm going to evaluate. So this means my volume is going to be approximately equal to how do we find the volume of a box? Let times times height, right? So basically it's the area of the box here. It's going to be, we call it the delta area, right? Times, we're going to take the sum of all these delta A's times our f of x, y's, right? So we're going to add up all these volumes. So basically delta A in this case is what? Here, delta A is 1. It's a 1 by 1 rectangle, so the area of each of these rectangles is 1. So this means my volume is going to be 1, which is my delta A, times the height. So it's the area of the base times the height. And the height is going to be given by these functions, these coordinates. So f of 1, 1 is going to be one of my heights. Another one is going to be f of 2, 1. Plus f of 3, 1, plus f of 4, 1, not 4, 1, plus f of 1, 2, plus f of 2, 2, plus f of 3, 2. So basically I'm just going to plug all these points into my formula. So what I've just done is found all the volumes and I added them together. And that's going to be my approximation for the volume under this surface. So the volume is approximately now, I'm going to plug in 1, 1. So it's 4 plus 1 squared plus 1 squared plus 4 plus, and I'm going to plug in 2 for x and 1 for y. 2 squared plus 1 squared plus 4 plus, I'm going to plug in 3 for x and 1 for y. 3 squared plus 1 squared plus 4 plus, I'm going to plug in 1 for x and 2 for y. 1 squared plus 2 squared plus, that was a 1 and a 2. So now I'm at 2 and a 2. 2 squared plus 2 squared plus 3 and a 2. 3 squared plus 2 squared. And whatever that give you would have been there. So there would be 1, 2, 3, 4, 5, 6 air volumes that I'm adding up, and that will give you the total volume. Right? So that's sort of the idea behind the Riemann sum. Here, the exact volume can be obtained by dissecting R into an infinite number of rectangles. So, right, this would just be an approximation. With 6 subintervals, if you want to call it that, or 6 subregions. But the actual integral is actually going to be given by a limit, right? So it's sort of this is the limit as I and j go to infinity of x I y j times delta a. Sum. Summation, I forgot the summation. This is a Riemann sum. You're adding all the volumes. F of x I, y, j times delta a. I goes up to n, j goes up to m. So the i's just tell you how I'm dissecting things horizontally. The j's will tell you how I'm dissecting them horizontally. So the i's in this case would be 1, 2, 3. The j's would be 1 and 2. Right? And I'm adding up all the volumes as my i's and j's run through the numbers. As I said, this is not the focus. It's good for you to understand what the integral is, but as for the specific, like this specific formula and all that stuff, I'm never going to ask you about, and you'll never see it on a test, on a final. But it's good for you to know where the idea is coming from, but we're not going to spend any time on it. We're going to sort of just jump into the shorthand way of doing things. However, it will be irresponsible for me not to tell you about this, so I can tell you about it. Otherwise, I might have to go buy a gun. Someone's gonna, like, why you didn't tell us about this, Jhevon? And then, you, me, in the schoolyard next week. 3 p.m. I will be there, because now I know. It will build up my strength. Okay. Okay, so, double, triple, etc. integrals are called, sometimes we call them iterated integrals. So you might hear that phrase, iterated integrals. And so now let's actually try to get into the meat and potatoes of how to do the shorthand. And trust me, if you thought Riemann sums in Calc 1 was annoying, the above definition is actually a legitimate pain. But luckily for us, it's similar enough to the old way of doing Riemann sums that all the formulas are still sort of the same. So our integration rules are going to look the same overall. It's just that now, just like in partial derivatives, we're going to have several variables to worry about, and one of the most challenging parts here is going to be setting up the region. And with rectangles, it's actually not that bad. So luckily for us, we can use our knowledge of single variables. We can use our knowledge the trick, it's not really a trick, it's just how it's done. Evaluate one integral at a time. And this is very important from the inside out. So, if I look at something like this guy, let's get it hard out there. A up to B, C to D, f of x, y, dx, dy. How we actually think of doing this is in parts, like a partial integration, just as how we had partial derivatives. I'm going to let this integral sit pretty out there, but on the meantime, I'm going to work out the inside integral. C to D of f of x, y, dx, right? I'm going to work out that part first, right? The inner integral first, and then worry about the outer integral with the result. While in here, I'm doing a partial integration. This means treat y as a constant. And integrate with respect to x. Right? So my inner integral, notice it's a dx integral. So I'm going to integrate the x functions and treat the y functions as if they were constants. Right? And then I'm going to have a result now. It's going to get rid of the integral because it's a definite integral. And then I'm going to integrate the outsides. Right? So we can sort of do in these multiple or iterated integrals just one at a time. It's very important, though, that you move from the inside out. That's just going to be the way we have to set things up. A, B, C, D are called the limits of the integral. If these are constants, that's very, 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 very important. If these are constants, we can switch them at will, right? So, for example, this leads us to what's called Fubini's theorem. Which basically says we can switch the order of integration, if there are constants, that is. When we will get to the level that we are putting functions on these guys, and when you put functions there, things actually change a little bit. But if there are constants, we can pretty much swap them and integrate who we want to integrate with respect to first. You can actually just make that choice. So copy Fubini's theorem. If f is continuous on a rectangle R, which is A cross B, AB cross CD, then double integral over R of the function f dA is equal to notice we can switch the order as we please, right? I can do a dx dy or I can do a dy dx. Right? Another thing I want to point out here, just to emphasize, then we'll do a couple examples so you can see this in action. The limits must match up. So, for example, if x goes between A and B, y goes between C and D, then we can say Notice that the inner integral has the CD, which is going with the y, so I must put a dy first, because this inner one must match with those limits. The dx will have to go second, because he will have to match with the outer limits, right? Or, if I decide to put the order the other way, I would have to put the dx first, and then the dy, because the x must match with a and b, the y must match with the c and d, right? So the order you're doing things in is going to matter. Okay. We actually know enough to do a couple simple integrals right now. So I know some of you might be lost in all this theory. Let's actually do it. Compute this. 0 to 1, 1 to 2 of the function xy cubed dx dy. And then I'm going to actually do it in the other order. Here, well, we don't see it yet, but eventually we're going to talk about why we care about the order in the first place. So, how do you think we're going to do this one?
We're separate
Right, so on the inside, I'm going to worry about this guy. So I'm going to have 0 to 1. What is the integral of this with respect to x? Right, half x squared y cubed, right? This guy is going to be a 1 and a 2, and my dy is just sitting out here, right? So I work on the inside first with respect to x. My y is just like a constant, he's hanging out. I integrate the x function, and the y function stays up. But the same fundamental theorem of calculus still applies, so I'm going to plug in the 2 on top, then the 1 on the bottom, and subtract them. So I'm going to take a 2, plug in here. I'm going to get 4 over 2, which is just 2y cubed, minus, take a 1, plug in here, and I'm going to get a half y cubed. I could actually simplify those. So this is 0 to 1 of 2 minus a half. This is 4 over 2 minus 1 over 2, so this is just 3 over 2y cubed. I notice right now I just have a single integral with respect to y, so now we're completely back into Calc 1, and I can just integrate this guy. So this is just going to be 3 over 2 times y to the 4th over 4. And I'm going to plug in 0 and 1. So if I plug in a 1, I would get 3 over 8 minus 0. So the result here is 3 over 8. Questions?
So I suppose the integration rules that we learned before would apply to.
Yeah, all the integration rules. Integration by parts, partial fractions, trig substitution, all that coming back. But we're all experts on it. That's Calc 1 and 2. So we're good. Substitution, yeah, everything. Everything's coming back. But now you're going to have to apply that to one variable and ignore the others and treat them as constants. So you're just going to have to put laser focus on them. Okay, I'm only going to do the trig sub on the x's. The y's are just hanging out. Yeah.
Does it always have to be over definite integrals, or can you do this with indefinite?
You can do it with indefinite. You could have a plus c. Yeah, that's fine. But for now, we're doing definite. We'll talk about indefinite and more.
Just to make sure, you were at x squared over 2 times y to the third. Did you, to go to the next line, did you already plug in 2 and 1?
Yeah, I plugged in 2 here.
Or
2 squared over 2 is 2, right? So that's 4 over 2. So that's 2. y cubed, minus, then I plugged in the 1. So I just get 1 half y cubed.
Okay. And then
Right, so I just applied the fundamental theorem of calculus to get here.
Okay.
And then now I have a single integral and I do it. Let's do the other order as an illustration. Let's do Fubini's theorem. dy dx. So what would this look like? 1 to 2 on the outside, this becomes
X, y to the 4 to the 4.
between 0 and 1. Leave the dx out here. We're going to apply the fundamental theorem of calculus, plug in the 1 into the y. Right. That's another place students might mix up. You plug it into the wrong thing. You have to remember what variable you're integrating to. I'm doing dy first, which means now my constants are going to be plugged into the y, not the x. So I'm going to take the 1, plug into the y. I'm going to get x over 4. Minus, I'm going to take the 0, plug into the y. And I'm going to get minus 0. That's dx. So now I just have the integral of x over 4 with respect to x. This gives me what? Integral of x over 4. X squared over 8 between 1 and 2. And then I'm going to plug in the 2 here. And what am I going to get?
4 over 8
I'm going to get 4 over 8
minus 1 over 8.
minus 1 over 8. And the result is 3 over 8. Right? Which is not a coincidence. It's Fubini's theorem. This will actually always happen as long as your function is continuous. So basically, what is that 3 over 8? What does that mean? How do we interpret that number, 3 over 8?
It's a volume.
Hmm? What?
It's the volume and the...
It's a volume, right? So in the x, y, z, if my x goes between a 1 and a 2, right? So here my x values is 1 and 2. That's just running along here. And my y value is 0 and 1. That's just running along here. So if I look at this rectangle here, right? And over here I have this function doing something, right? This is my function z equals xy cubed, doing whatever. If I were to find the volume under this surface that hovers over that rectangle, right? So I'm finding the volume of this part. That's what I just found. So the volume of the guy that looks like this is 3 over 8. Right? I just found the volume. That's what I just did.
But it's the same way with the single integral. It's not the volume if it's not entirely over the...
Right, so if my function actually dipped under the xy plane, I would get a negative volume. That's why I call it the net volume. Right, but here my x's and y's are positive, therefore the z values will always be positive. So in this case, it's completely the volume under.
And when we have problems like we did in single variable, we'll say like find the volume of it, and they want you to like break up the integral. Like, where it's positive.
Rarely.
Yeah.
Rarely. If they do ask, you should know how to do it, but I don't see that a question like that being asked often. But yeah, if they do ask you to find the volume, then you should always make sure whether your function is always positive or does it go negative somewhere. And if it does go negative, does it go negative over the particular region? If it went negative somewhere else, it doesn't matter to me, right? But over this particular region, does it hit negative values? Then you're going to have to turn those values into positive values. there are going to be situations where one order is going to be difficult to evaluate and the other order is not. And there are going to be situations where one order is impossible to evaluate while the other is not. Right? So Fubini's theorem is really important for that reason. Sometimes switching the limits can do a lot of good. So for example, since a certain order difficult to impossible. It's hard to give an impossible one here, but I'll see one soon. In fact, on your quiz there was one. Maybe I'll just jump ahead and show you that example, but we have to come back to it. An example of that would be, what about this rectangle, this integral? Y cosine xy dA, where my R is defined as the region 0 to 1 by 0 to pi. In this case, one order is difficult. Well, relatively difficult compared to the other one, right? So there are a couple ways I could set this up. Note, we could do, I could do 0 to 1, 0 to pi of y cosine xy, and 0 to pi goes with dy dx, or I could actually do 0 to pi, 0 to 1 of y cosine xy dx dy. Which one would you do?
Second one,
The second one. Why?
there's only one x value.
There's only one. Notice that here, if I did this one and I'm integrating with respect to y, there are two y functions. I'd have a y times a cosine of y, right? To do that, what would I need?
We can use all like the same like tools we use. Like,
Yes, the same tools.
so I would do like you do like I could name it say y 1 0 and then cosine x y x. It would be like
You're talking about the tabular method?
yeah.
Yeah, but what is that from? What's the main method? Integration by parts is how you do it. I heard people saying product rule substitute. It's an integration by parts problem, right? To do that, you guys need to review your Calc 1 and 2. It's coming, right? It's going to be really bad, right? That's an integration by parts problem. But here, with the dx, what is it? There's no integration by parts. I'm just integrating the cosine, right? This y is like a constant, right? So he doesn't matter. Here, the cosine is my only function of x. However, if I'm considering as functions of y, there are two functions of y being multiplied. I need by parts here. I wouldn't need by parts here, right? So I would actually do this one. This one is easier, right? So I would actually try to compute this r y cosine x y dA. I would actually use the second way of setting this integral, 0 to pi, 0 to 1 of y cosine xy dx dy. So that's 0 to pi. What's the integral of this with respect to x? Sine xy times
Negative y squared. Wait, no. I went the other way.
X squared y
Hmm?
X squared y over 2?
Well, I have that y sitting out here, right? But
Oh, is it over y?
over y, right? Between 0 and 1, dy. So here, now my y's cancel. So it turns out I won't have to use by parts after all, because I did the x first. It actually got rid of the problem for me. Now I'm just going to plug in the 1 into the x value and 0 into the x value. So now, plug 1 into the x value, I just get sine y. Plug 0 into the x value, I get sine of 0, which is just 0 dy. So now I have that stupid little function. I avoided having to do integration by parts by choosing a nice order. Integral of sine minus cosine. So this is negative cosine y, 0 to pi. I have minus cosine pi plus cosine 0. What's cosine of pi? Huh? Cosine pi is negative 1, therefore negative cosine pi is 1 plus cosine 0. It's also 1. Guys are taking too long, so the result here is 2. So choosing the order can actually make your life a lot easier, right? I mean, we struggle through that. Imagine if I had to do an integration by parts. Well, I was going to talk about that example I gave on the quiz, but it actually falls into the next section anyway, so I won't.
Jhevon?
Yes.
For when you substitute the 1 and 0 for y, it's not sine y.
I substitute for x.
Okay,
I did dx.
The third one, it's not sine y minus sine 0, it's sine y minus 0.
It is sine 0.
Yes, I said sine 0 is 0.
Oh,
Yes.
gotcha.
So I just plugged that in. So maybe I'll talk about the quiz problem in the next class. Well, class after the next class maybe. For now, I'll just give you some properties. Yes, review your integration techniques. Very good intros. Luckily for you guys, I'm also teaching Calc 2 this semester, and I'm killing them with integration right now. So you can probably watch the videos for those. In fact, I've done most of the techniques so far. Just polar coordinates we haven't covered. But I went through substitution, integration by parts, partial fractions, all that, trig substitution, trig integrals, all that. It's already been done this semester. Yeah, let's look at some properties. They're very familiar to single integrals, so it's not any big news here. If I'm integrating a sum of functions, then integrals distribute across sums. Double integrals do it just as how single integrals do it. Right, so plus or minus, I do plus or minus here. If I have a constant times a function, dA, again, constants can factor outside, that's not a problem. So I can do it that way. Of course, if I have f times g, like a multiplication of functions, what can I do there? This double integral of f times double integral of g. Is that true? It's not true, right? But people do it all the time. Make sure you never do this. This is blasphemy. You do this anywhere, you get a 0 for that problem. Okay? A lot of people will see something like x squared y dA, and they do something like, oh, x cubed over 3, y squared over 2, and then start plugging in limits. No. Right? You don't just integrate each piece and stick it together. It doesn't work, right? Just make sure you don't do that. We also know the function another property that I want to talk about. If f of xy is greater than or equal to g of xy, then their integrals will share the same relationship. Then the net volume under f will be greater than or equal to the net volume under g. So this helps us with a lot of comparison theorems. That actually ends section 12.1. Homework is not due though, because next class we have a test, study for the test. But the homework for 12.1 will be due the following Tuesday. We'll stop there if there are no questions.
So, like, after the exam.
After the exam, review your integration techniques.
Or you got one and two.
Yeah. It's gonna be very important.
We have a lesson and we just go home.
After the test, maybe a small one.
Do you think?
Maybe I'll talk a little bit more about integrals.
Do you think? Since I'm just wondering. If,
The test is an hour and 15 minutes long. It's pretty much the same kind of format. 5 problems.
No, so for the test, but like, because since we're gonna go over this stuff, I don't know, like, maybe we could see you after the exam, go over, like, integrals and stuff like that. So
Maybe, yeah, you can see me anytime. Just go to the theory. Okay, we will stop there.
So